All right. Hi, everyone. Good afternoon, good morning, good evening, wherever you're joining us from, and welcome. Welcome to our ARM AI Tech Talk series. This is the place for the latest and greatest in AI, whether it's trends, technologies, best practices, whatever it is from ARM and our ecosystem. And it's great to have you here. It's coming up to Christmas. It's coming up to December. So as you can tell, I've got my Christmas attire on. We are very excited to be finishing off the year on such a high with this fantastic talk today from ARM and our ecosystem engineering team. Yeah, it's great to have you here today, whether you're joining us on YouTube or on Zoom. It's great to have you wherever you're joining us from in the world. I've just got a couple of little housekeeping things to go through first and foremost. If you've been to one of our tech talks before, you know the drill. I've just got to go through a couple of little things here just to make sure that everyone's familiar with how they can get involved in the conversation. So if you want to tweet us at ARM Software Dev, you can use the hashtag AIVTT to do so. We've done well over 50 of these ARM Tech Talks. It's been a phenomenal success, and we're really thrilled at how many of you, how this has resonated with our audience. If you like today's talk and want to watch any of the past ones, you can do so on our ARM Software Developers YouTube channel. I'll paste a link to this in the chat later on in today's session. And you can also sign up for our next AI Tech Talk at arm.com/tech talks. We don't yet have the schedule ready for early next year, but we are working on some very exciting new topics, a brand new platform, and a lot more. So there'll be a new look and feel to the Tech Talks. We'll have a new platform, so we will be moving away from Zoom and bringing new topics as well for you to hear about. I'm really, really excited about this. We're going to share our plans with you shortly, so keep an eye out on your emails for anything on that. You'll find out all the registration links, and the website will be updated as soon as those tech talks go live. We've got some very exciting ones coming up in January, February, right through next year. So at this point, I normally hand over to one of our presenters and one of our guest speakers. I will do in a second, because the majority of today's talk will be from my colleague, Kshitij, in the ML ecosystem engineering team. But unfortunately, you've got to hear a bit more from me at the beginning. And you may have attended a few of these talks before and gone, who is this guy hosting these from ARM? Who is he? What does he actually do? So I'm Tobias McBride. I'm an ecosystem product specialist here at ARM. And I'm also really honored to be a product manager for this incredible ecosystem engineering team today. And Kshitij is one of the people, one of the engineers from that incredible team, who's going to be talking to you today about how you can get started with AI at the edge. So before I do a little bit of a kind of background setting and context setting, Kshitij, why don't you just go ahead and introduce yourself to folks on the call?
Sure. So yeah, my name is Kshitij, and I work as an engineer in the machine learning ecosystem team. So yeah, my background is mostly embedded, but yeah, from time to time, ecosystem engineering team gets to tinker with lots of different stuff. So yeah, that's me.
Thank you so much, Kshitij. So if you want to get involved in the conversation, please do use the Q&A box and ask any questions you've got at any time. We'll get to those probably at the end. We've got a very exciting demo for you today, a very exciting little worked example and demo that you will be able to try immediately after the talk. So do keep an eye on that. It's going to be very exciting at the end. I've just got 5-10 minutes max of bit of context setting and high-level setting, just to give you some context of where we're coming from today and why we feel this is so important for our ecosystem and for you as an audience. So if we look back historically at the IoT software ecosystem, there has been a fair amount of fragmentation in the past. You know, how do you select between different IoT and support the different IoT stacks, RTOS, cloud, software components? You know, you want to connect to the cloud. How do you connect to the cloud? That adds new complexities, different connectivity stacks. You've got to protect against a whole new class of remote attacks and secure yourself against vulnerabilities. And security, to be honest, needs to be considered right from the start. You need to be able to deploy your software at scale and make sure you invest in the right type of differentiation. So when we look at this, we think, well, that's what's happened historically. And as we look ahead, we see a real opportunity for us to overcome these hurdles and for ARM to be at the right at the center of this and work with our ecosystem to help scale, to help accelerate time to market, and help reduce barriers to entry and reduce overheads in this. And so that's why we came up with ARM Total Solutions for IoT. We introduced this to remove the barriers that block growth in IoT deployment, because when we look at all of these components combined, and I'm going to touch on a few of them in detail here today, we believe that when you look at these components, they're going to help accelerate product design cycles by as much as 2 years and substantially reduce fragmentation and increase developer velocity. And where does it start? Where are we going to start here? Well, we're going to start with the ARM Corestone platform. The ARM Corestone subsystems, they're pre-designed, pre-integrated, pre-verified hardware subsystems. They target specific use cases and they're available across Cortex-A and Cortex-M ARM IP. And how do we make those available? Well, we make them available as part of our ARM virtual hardware offering. These ARM virtual hardware targets are yes, a virtual representation of our Corestone subsystems, but they also comprise third-party ecosystem boards from our ARM partners, which is really exciting. So you can functionally validate your software, whether it's on those Corestone subsystems, or depending on your use case, you can also validate your software and functionally test your software on our third-party ecosystem boards that we've made a selection of available in the cloud on our virtual hardware. And to bring it all together, we have two initiatives, Project Centauri and Cassini. Project Centauri is an ecosystem initiative that really delivers and focuses on software leverage and scale with defined standards and security frameworks and abstraction from RTOS complexity. And Project Cassini does the same abstraction and focus on security for Linux applications. And so as we look at all of this, I'm really going to focus on this initial kind of context setting on ARM virtual hardware and Project Centauri, because this will really form the context for what Kshitij and the team have been working on later on in the demo that you're going to see. So what is ARM virtual hardware anyway? ARM virtual hardware is a functionally accurate representation of an ARM-based SoC, or ARM Corestone platforms, or even a third-party hardware development board. It all runs cloud natively. It scales easily in a modern cloud-based development workflow, whether that is through CI/CD or ML ops. And as such, it's suitable for all IoT workloads from an MCU right through to the intelligent edge. And because it's all virtual, it's simple and scalable way, in a simple and scalable environment, we are able to remove dependency from RTL or hardware and really unlock the true potential of cloud native development for you, for our developers. And so you can functionally validate your software in the cloud. And whilst we're not saying it's going to replace physical hardware, far from it, we're saying this is a great complement to it and really enables you to supercharge and scale your tests in a much faster way than ever has been possible before. Project Centauri is the other bit I want to focus on. So Project Centauri is our Cortex-M software initiative, and it's designed to develop and drive open and secure standards into the market and make it easier for developers to build and update IoT applications. So by working with our ecosystem, we take a standards-based approach to software and security, and we want to make sure that you can expedite adoption, reduce barriers to entry, and really allow the IoT to scale. So we have three kind of guiding principles here around open standards, and really focusing on proliferating those open standards, solving real world problems that you tell us about, and we want to hear from you about what those are and developers tell us about, and working across the ecosystem to produce those free open source solutions. And whilst this is a big goal, we have, and indeed have focused on one use case initially, which is secure firmware update. This standards-based approach is easily scalable across other use cases. And as the initiative continues to mature, we will do so. So this kind of standardization piece is really what I want to focus on here, because the next level down, as you can see, one of the components here is CMSIS. So we're going to focus a bit on CMSIS here. Common Microcontroller Software Interface Standard. I quite like the acronym. For short, having to say that a few times is going to be quite difficult. So CMSIS is a collection of API definitions, libraries, utilities, and methods that simplify and accelerate the creation of microcontroller applications. Many of you on the call, I'm sure, have heard about it already. For those of you who are new, this is exactly what it's all about. And it provides a standardized building block environment for your software, and it's available for all Cortex-M and select Cortex-A processors. And this software pack approach to distribute device support, software components, and more is all open source and has been really successful. As you can see on the left-hand side, thousands of devices and millions of projects. So it's great to see how successful this has been. And we're really excited for you to take advantage of it and to show you how you can do that later on in today's presentation. As part of this, I want to focus on Open CMSIS-Pack. These software packs and this project and this initiative delivers an infrastructure that enables you to integrate and manage software components, and really focuses this standard on code reuse across embedded and IoT projects. Because as I mentioned at the start, that software compatibility that I spoke about for component reuse, and it's long been a challenge in the microcontroller space, especially in IoT. And so this Open CMSIS-Pack approach provides an effective packaging technology that currently supports around well over 9,000 different microcontrollers, and as such provides that delivery mechanism for various software components, device parameters, evaluation board support, and much more. And this kind of standards piece here is what we're focusing on as well. So you've got ARM virtual hardware to functionally validate your software in the cloud. You've got Project Centauri, and particularly today, focusing on CMSIS and Open CMSIS-Pack. These standards approach enable you to reuse components, reuse your software, and improve portability of software across embedded and IoT projects. And so before we dive into a demo, of course, we've got to try and bring this all together. And to do a great demo, we need a great IDE. We want to show off in an IDE here. And to do so, we're going to use Keil Studio. Hopefully some of you have used this. Keil Studio is our next generation IDE. It's all browser-based. It has a browser-based editor, Git integration, compiler service, and debugger, as we've put here. And currently it's in an open beta. It launched earlier this year, and anyone with an ARM or Mbed account can access Keil Studio for free. So do check that out afterwards if you want to use Keil Studio Cloud. It's all free to use. And so we thought, well, why don't we actually show how you can use this all together? Why don't we show you how you can use CMSIS-Packs to create your own applications? Combine that with functionally testing and validating your software on ARM virtual hardware. And then combine that with doing so in Keil Studio, and how this all fits together under ARM Total Solutions for IoT and Project Centauri. And so I've been really fortunate to work with this team well over a year now as a product manager, and learned a lot from them in the process. And one of the things we've been really focused on in the last few months is CMSIS-Packs. And in particular, as you're going to hear about, there are these ML examples that are available to you today as developers. And you can go and we're going to tell you how we refactored them as part of ARM Total Solutions for IoT and made them available as part of ARM Total Solutions for IoT, refactored into being CMSIS-Packs, and really show you how you can do the same. Whether you want to take our own CMSIS-Pack examples, and we'd love you to do so, and try these out yourselves, and be inspired to then create your own, and show you how you can then use them together with these incredibly powerful modern development tools like ARM Virtual Hardware and Keil Studio. And so let's bring this all together. And so that's enough context setting for me. It's now over to Kshitij to talk you through what we did and what the team did an incredible job doing, and how this all plugs in together with ARM Total Solutions for IoT and Project Centauri. So Kshitij, I will grant you approval of controlling my screen, and it's over to you for the demo.
Okay, thanks, Tobias. Let me check if I can control and switch over to the next slide. Okay, before we jump to the actual demo, for those of you who are new to MLEK or ML Embedded Evaluation Kit, yeah, we'll just give you a brief introduction, but I promise not to spend too long on this. So, Machine Learning Embedded Evaluation Kit, MLEK for short, is an open source repository, and it has several end-to-end ML examples. The idea from the beginning has always been to provide an easier entry point into this world, running ML workloads on embedded systems. Typically, all the software components, there are various different examples in different places. But yeah, we try to consolidate the software stack and package it up as a CMake project. So these are the examples which are currently available. So the three kind of broad spectrum of use cases: voice, vision, and vibration, and the different examples available within each. Important to highlight, so even the models that we are using within these are all Apache 2 license, available from publicly available ARM Model Zoo. There There is one exception, the object detection. It is available from EMSA-VS. They were the ones who contributed this use case. So yeah, we welcome other contributions as well. And the last use case here, which doesn't fall into any category as such, is the inference runner. And this is primarily to experiment, to deploy your own custom neural network model. If you've trained something on your own and you want to experiment and see if it runs with the software stack, this is the kind of experimentation tool you have available. So when we started, primary goals of the evaluation kit, and these haven't changed massively. So the goal was to consolidate the software stack. So I've spoken about this before. I've listed the dependencies on the slide deck there. So we are heavily using CMSIS-NN, CMSIS-DSP, and the CMSIS core. And the main inference engine is TensorFlow Micro. And being an evaluation kit, I mean, the first thing that we needed to do was to enable or facilitate performance evaluation of the upcoming ARM IP. So this has been the focus for us for a long time, primarily towards Ethos-U, the ARM's micro NPU. But if you're using the FPGA platforms, you can do a performance evaluation for Cortex-M systems as well. And as I spoke about on the previous slide, the inference runner skeleton use case sort of a thing, which allows you to deploy your custom neural network on any of the systems we target. So our main targets are ARM reference designs. So Cortex M55 paired with Ethos U55 or Cortex M85. They are packaged up within Corestone 300 or 310 implementations. So as Tobias spoke about previously, we run on ARM virtual hardware, and same software essentially can run on the FPGA implementation as well. So this is really useful for us as developers, because we don't have to deploy everything on the FPGA on the physical targets. Everything can be tested in CI using ARM virtual hardware. So all the verification is done using the reference platforms in this environment. We also do support native execution, which is to say that you can compile and execute the ML examples on your host machines. You don't need to cross-compile them for different targets. And this has been the case from the beginning, since MLEK was first published, because we wanted extensive testing framework to test out our ML use case logic, which can run natively, because TensorFlow Micro can be built for your x86, 64, or ART64 targets. And it's easier to debug, obviously, than to debug an embedded system. So that was a brief introduction, and we'll move on to how we have refactored the repository to publish CMSIS-Packs, which we'll be demoing today. So we started with, I think 6 months ago, we started the refactoring work where we just had evaluation kit on mlplatform.org, and we published a CMSIS-Pack, which is a platform agnostic use case API. So it has all the machine learning logic required to run all the use cases mentioned in the previous slides. And same sources are available as an API library, which is just a CMake managed library, and you can build it or integrate it within your own projects. So the idea with these two offerings was that it can cater to the different requirements. So the API library, for example, can be used with existing third-party projects, and it can be used by ARM Total Solutions, IoT, which is what MLEK is geared up to support. And with the CMSIS-Packs, we can support existing IDEs, which have support for CMSIS-Packs already. So many of you might be familiar with Keil Microvision or ARM Development Studio. And new tool that we'll be checking out today, the Keil Studio Cloud. CMSIS-Packs makes it easy for any developer developing for any kind of physical target to use our examples and develop their example on their the physical target of their choice. So most of the refactoring work actually was to extract out this ML use case API logic from the original evaluation kit, where it had calls going into some hardware abstraction logic. It was dependent on hardware, like we were displaying things on the LCD for MPS3 board, etc. And to make this platform agnostic and the only dependency to be TensorFlow Lite micro engine was done basically so that we can support any physical target. Like this ML business logic shouldn't depend on anything hardware related. So whatever target TensorFlow Lite Micro can be built for, the ML use case API can run on that. And as we will show today, the idea was that this API will plug in as a component in your project, where you will have your own PSP or DFP. I should clarify, PSP stands for board support package, and DFP is device family pack. So these are existing CMSIS-Packs available for different evaluation boards. I think Tobias touched on it before, that there's support for more than 9,000 MCUs of like evaluation boards in CMSIS-Pack form. So the idea is wherever you have this layer available, you can actually build an ML use case. So where traditionally, even 6 months ago, our use cases could only run on Costone 300 or Costone 310. Now we are able to run on M3s, M7s, anything that has capability to run an ML workload. So what does our CMSIS-Pack actually contain? So yeah, this is just a description. On the left, you'll see that we have the API, which has two components. The common is basically general utility type functions, classes. So we have for audio examples, we have MFCC calculations. For images, we have conversion of the images to int8 or bounding boxes utilities for object detection, for example. The use case themselves are APIs which offer pre-processing, post-processing, and model classes for each ML use case. And then there are other dependencies. So the common API, for example, depends on some mathematical functions. And this is just our wrapper to kind of isolate CMSIS DSP. And we have calls going into CMSIS DSP for FFTs, etc. So sine, cosine, vector functions from CMSIS DSP are all consolidated here. And just a header-only logging utility that we rely on, so we don't have to keep changing printf calls, etc. That's the link to the CMSIS-Pack. It's available for you to experiment with from Keil page. And this is what it shows up as when you, for example, import it into your ARM Development Studio or Keil Microvision environment. On the top left, you see that there are different checkboxes you can enable. So if I were to develop a use case for keyword spotting, I would click that, and then it'll go through a dependency tree and ask me to choose that I need common math functions, I need logging ability, etc. And once you have clicked through those, you have these sources available for use within your project. So with this, we are at a stage now where we offer two different paths. So earlier we were limited, where we were only offering the choice, which is there on the left side, where MLEK was just basically a CMake, a big CMake project. And it was supporting only the up and coming reference designs. With CMSIS-Packs, we are able to offer users choice of developing for any physical target. So we can run on M7s, M4s, Cortex M33s, etc. The right side mostly is where you have a stable verified software stack. So where we were developing previously on up and coming targets, the choice on the right side basically allows users to have verified pieces of software which are known to be working and develop on top of that. So there's less debugging to be done. You only have to debug your part of the code because all the CMSIS-Packs that are available should already be fairly stable. And it offers easier integration. You don't have to do as much as you would have had to do with command line or CMake-based system to have support for your target. So it's an easier, more stable path to development in a lot of ways. The first choice is still used. For example, if you would be developing for a target which is not mature yet. If there's an FPGA target, if you were porting RTL to customize, for example, then yeah, the left side is still usable, but where there are stable CMSIS-Packs available, I think the right side, the CMSIS-Pack method is the method of choice. A bit more about Keil Studio Cloud. I think Tobias has mentioned that yeah, it's a freely available tool. You can use it now if you have an embed account. So yeah, I'll probably post these links in the chat later on as well. But yeah, it's a good tool, especially because it has support for ARM virtual hardware integrated. We will cover this in the demo as well. There's a link for R examples. It's available within ARM examples, MLEK course on 300, examples.kit. Important thing to note here is that whatever runs on Keil Studio Cloud, whatever you can build in that IDE, you should be able to build locally in your on your host machine as well, because there are command line tools available, and there's integration with Visual Studio Code. It's available as a plugin that you can install, and that should give you a fairly good environment to develop with CMSIS-Packs. Okay, this is, I believe, a quick introduction to Keil Studio Cloud. So let me see if I can play.
Oh, Shittage, you're on mute. So I was just trying to get to the mute button.
Sorry. Yes. Yeah, we will cover some of this in the demo as well. But yeah, as I said before, the main kind of standout thing for me using Keil Studio Cloud was integration with ARM virtual hardware. So this is just a snapshot which shows running on Ghost on 300 target. That you build it and you can execute it within the same environment, which is really cool. And the integration with Visual Studio Code as well via plugin extension. And yeah, you should be able to just build your project using the buttons available within this IDE. So we'll cover this also. So the first thing, the example that we have available upstream, which everyone should be able to experiment with. And let me try and share my screen at this stage. Let's see. Okay. Hopefully that's coming through fine.
Yep, looks good.
Okay, so this is our example, which is available on GitHub, and it's been imported into Keil Studio. That link, which is there on the slide deck, and it's a collection of two use cases: keyword spotting and object detection that can be deployed on ARM Ghost on 300 using Ethos U55. So just to see if I can actually run it. So the project I've built before, so it should just start on ARM virtual hardware, and it shows me some model parameters, the input sizes, and keyword spotting use case has one baked in input, which is the keyword down, and it's just an array of 16-bit audio at 16 kilohertz. And yeah, I have the two model files there, which is keyword spotting micronet medium, and they have been optimized to run on Ethos U55. So as you can see, I've had the output from ARM virtual hardware already, and it's detected keyword down with a score of 95%. So a quick look at the project itself, and this is all managed via YML files. So there's a C solution YML, and you can have multiple projects associated with this C solution file. So I'm using ARM compiler 6. I have my flags for linker and compiler, and these are the CMSIS-Packs that I'm actually using. So I'm using the CMSIS core pack. I'm using both support package for Ghost on 300 target, and I have TensorFlow Lite Micro related CMSIS-Packs, and this one is the pack that we have published, which is MLEK's use case API. And because I need to run on Ethos U, I also have the driver for this NPU. I could choose to run it purely on M55 in Ghost on 300, in which case I can remove this dependency altogether. And there are two projects, as you can see, object detection and keyword spotting. We will have a look at these project files a bit later. So this is the vanilla project that is available, but the thing which we wanted to show you today mostly was that once you have verified your application logic, your machine learning logic on ARM virtual hardware, it's fairly straightforward to actually deploy the same example on a physical target, which is what we aim to do with our refactoring work. So that's the test essentially for the CMSIS-Pack, that it's able to cater to multiple targets. So I will switch over to a project which has been derived from this upstream repository, and in this one, I have added support for physical targets. So previously, where we supported only Ghost on 300 or Ghost on 310, I've added support for a Freedom, NXP Freedom board, and STM Discovery board. And we can have a look at keyword spotting project now. And while previously we were using a WAV file baked in into our input and into our application, we have an option of using the onboard microphone for SD micro board. So we have two different pipelines now. One is WAV file based and one is live audio based. That's the only difference. And you can, it's really nice to be able to select different targets for different files. And the model I'm using, while previously I was always running on U55 or U65 NPUs, now I'm only running on Cortex-M system. So I'm using the vanilla TensorFlow Lite Micro file, and this will run on the Discovery board and the NXP Freedom board. A bit of linker scripts for different targets, and the common device layer. So this is also something that has changed, because yeah, the upstream project, it's both goes on 300 and 310 only. In this one, I've just added support for different devices, and this is where the magic happens. So this is the device layer. It mentions which components are being used from the CMSIS-Pack. So the CMSIS-Pack is mentioned at the top level C solution file. Previously, we were using only the BSP for Coast on 300. Now you will notice that there are additional packs here. So this one for Coast on 310. This one is for NXP Freedom board, and sorry, these two are for NXP Freedom board, and this is the one we are using for the SD Micro Discovery board. So that's a device family pack. And in the device layer, we mentioned components which are being used from the packs mentioned at the top level C solution file. The good thing here to note is that all of these are actually not specific to this discovery board. The components that I would need to change if I were to port this example for a different discovery board would be only the ones here at the bottom. Because these are just hardware abstraction layer components, they should work with all discovery boards. So now that I have this keyword spotting working with one of the discovery boards, it would be actually very, very easy to port it to several others, which are supported by this device family pack. Okay, so yeah, I have my board connected, and I think we saw this in the Keil introduction video as well. I have this device here, and I'll connect to it, and hopefully I should be able to debug. So if the project has not been built, it'll go away and build it. So you can see my build log up here. Okay. And yeah, while it's going through the process of flashing, we can look at what the main logic is actually doing. So this will also give us an idea of how we are using our CMSIS-Pack. So good thing, the only thing that is platform dependent is the call to board initialization, which comes from the device layer. So this will be in source files here and coordinate.c and the function. So everything that I need to configure my hardware is here. So I'm doing the boot up low level initialization, and I'm initializing the UART so that I can direct my printf. And then I'm initializing the model. This micronet keyword spotting model is part of the API. So you go about initializing it, do some housekeeping, managing input and output tensors, just checking their sizes, etc. And the main logic for using the ML workflow, ML pipeline, are these. So this is fairly, I think, uniform in all of the use cases. So you have pre-processing, post-processing, and running the inference. Okay, our debug session has started, so it has stopped on main. So I should have a breakpoint somewhere here already, and I can go about running it, allocating tensors. And this actually, yeah, this is in my model class, which comes from the use case API itself. Let me go back to the top level. Okay, so at this stage, I've recorded some audio and I'm able to look at the different variables. I can look at my core registers, etc. Yeah, in debug mode, actually, because I'll be missing a lot of audio, it won't work. The keyboard spotting itself won't work very well. So yeah, we will let it continue. Move the breakpoint. And we'll move over to looking at the same project in Visual Studio Code environment. So let me stop this debugging session. Move over. Okay, so the same project, and I have the extension pack installed. So I have this this view available to me. So I'm able to build, flash, debug, open serial connection. It's really cool to be able to just do this. My board is connected, and yeah, I know this thing is running from my previous session. So I will clear. I will go and close that session first. And I will. Oh yeah, it is already connected, which is good. Let me open a terminal. So thing to note here, whatever backend tools are being used within Keil Studio Cloud environment, the same tools are available natively to be used on your local machine. So, for example, I should have access to C solution, C build, which are being used to generate the projects and generate the YML files, XML files, which are actually being used to build the project files. So I will generate the projects, which will go away and generate all the combinations of my projects. So I have object detection for my COSM 300, 310 targets. I have keyword spotting for STM discovery board. So this is what I'm interested in. So we saw the debugging in Keil Studio Cloud. In this one, I will build it in release mode, and I will deploy it. Okay. And I should be able to flash this. Should run fairly soon. And while it's doing that, let's see if I can pick this up. Hopefully that's coming through okay. Okay, it's running.
Just to prove it's live.
Yeah, so if the demo gods are with us, it will work, but usually as things go, it doesn't. Stop. let's see, left. Yay. Okay. So yeah, it does recognize keywords. It is running live. Down, up. Okay, missing some keywords, spotting some, but yeah, the whole idea that it's actually running live on the board. Yeah, that's mostly it. But the summary or the key takeaway is, it took me actually less than a day to add support for a physical target from where I started with support for virtual hardware. So this is mostly to show that, yeah, it's quite easy, it's straightforward. Once you have verified your application logic using ARM virtual hardware, to move to a physical target and deploy on multiple targets seamlessly is quite easy with the new tools and with this whole package ARM is offering now. Okay, I will stop sharing my screen. Tobias, are you okay to share back the slide deck?
Sure.
Okay, quick word on future work. So yeah, the example that we've shown today, we are hoping that we will be able to upstream this, so you can also play with this. But yeah, please go and check out the existing example for CoreStone 300, and yeah, you should be able to run it on ARM virtual hardware. Support for CoreStone 310, that's fairly trivial. That will also come along with the support for physical targets. And we will have a new exciting semantic segmentation use case API being published with our CMSIS-Pack. So there will be an example based on that as well. That's it from me. You are on mute, Tobias.
No, I'm the one on mute. We've both done it. There we go. So the demo got shone, but I finished off the year as I started on mute. So thank you so much, Shittage. That was awesome, and a great way to show how you and our developer community can and wider can use the CMSIS-Pack, ARM virtual hardware, Keil Studio, bring it all together and do this yourselves. So I've already pasted a link to the example in the chat. All of the links from today and all of the slides from today will be available within the next 24 hours on developer.arm.com in our kind of slide repo where we keep everything. So do check that out. You will automatically get an email a couple of days time telling you the slides are live. So go and check it out there. And the recording from today is going to be live pretty much immediately because we're live streaming to YouTube after this. So do check that out and let me know, as ever, reach out to any of us if you've got any questions. So we're going to just pause there, let you have a look at any links, and then we're going to jump to some questions. So let me just load those up. So let's have a go at, let's have a go at, when using CMSIS-Packs as opposed to CMake, does it integrate nicely into CI/CD type workflows such as GitHub Actions? From what I understand, it integrates pretty well, right, Shittage?
Yeah, that's right. I think there are several examples available already where we are doing this. Even the example that we showed today, actually, we are building it in RCI, and there's no reason why it cannot run on an external GitHub Actions triggered CI node as well.
Yeah. Brilliant, thank you. And do keep your questions coming. We've got probably about 10 minutes for questions, so hopefully enough time. And again, do reach out if you've got any questions afterwards. Question here, is it possible to connect devices at my desk, perhaps via USB Connect? What about LEDs, buttons, and other physical type interfaces? I mean, you were connecting the board right there, weren't you, Shittage? So, but I don't know if you want to expand further on kind of how that all works and whether you can connect other physical items.
Yeah, it should be. So anything that supports CMSIS-DAP, SD links, there's a list of what debug kind of links we support. But yeah, fairly everything that you were able to debug using traditional IDEs, you should be able to debug using web USB. The only kind of limitation probably is the browser you use. So your browser should support. So for example, if you noticed, I was using Google Chrome when I was debugging on SD microboard. I wasn't using Firefox because it wasn't available. But yeah, there's no there's no limitation as such with what you can do with it.
Gotcha. Thank you. And Joanne, I mean, I'll ask you this question, Kshitij, but if you've got any further clarification you want to ask Joanne about this one, then do please ask. And then Joanne, you can ask a separate question in the Q&A box. Can you talk about inference time on different target microcontroller and NPUs? So obviously it's quite a broad question. Is there anything you want to answer initially, or maybe add a couple of clarifying questions on that, and then I can answer those in the chat?
Yeah, I think we haven't, like, for these examples we've shown today, we haven't actually profiled, but judging by like very high level this thing on SD microboard, which is an M7 with all the extensions, it's taking per inference about half a second. So we are overlapping half the window for the previous audio and then pushing it in again. On an NPU, you could have run probably 200 inferences a second. So that's the kind of scale we are talking about, the spectrum. So obviously, if you're running on lower clocks, predecessor of M7, then yeah, things will look slow as it is expected. But then there are other tweaks you can make. For example, we are using keyword spotting, which is medium size, so it's about 182 kilobytes. The model. There's a smaller version available, which will probably run quicker, and probably you will be able to average results out. So there are different combinations of things you can tweak to make things run quicker on different targets. But yeah, quite a big spread there between NPU and different M-class CPUs.
Exactly. No, definitely. And in terms of the questions coming about, how can I feed reactive data streams to the devices? So I guess you were feeding in microphone input there. Are there other inputs that are supported that you know of? Again, if we can obviously ask questions further with our team if we need to go any further. But
yeah, so anything which you can read off peripherals of the board you're using, it can even be external. So I know for example, SD microboard has in their device family pack itself, they have support for certain cameras, so you can integrate those. So it's not available on board itself, but yeah, you should still be able to feed in other inputs, microphone jack, different cameras, USBs, yeah, all sorts. So this is actually not related. This doesn't come from our CMSIS-Pack. I should clarify that this comes from the device family pack for the device itself. So it'll be SD Micro who would be contributing this code. There should already be some support for the peripherals that you can read from.
Gotcha. Brilliant. Thank you, Kshitij. And then probably got time for one more question after this. Do you require specific OS and external libraries to run these ML examples on top of TF Lite for microcontrollers? And again, as this is a part of Arm Total Solutions. So is there a specific OS you require for these examples?
No, there is no requirement. It is completely platform agnostic, which is what we try to do. So from the beginning, our applications were all bare metal, but there is no reason why they can't run. If you were running some RTOS, you can just use these files as they are. You shouldn't need to do too much. Yeah, there is no limitation. It's pure C++ code.
Amazing. Well, thank you so much, Kshitij. We're just coming up on the top of the hour, and we're going to just wrap up there. So that was just a fantastic demo, fantastic example, and to show you how you can do this yourself, within half an hour of worked examples, slides, and a demo is just fantastic. And the team have been phenomenal in pursuing this over the last 6 or so months, and really producing fantastic work that now integrates incredibly well into Total Solution, is delivered as part of that standardization and IoT deployments piece that we've been speaking about earlier. So Kshitij, fantastic work from behalf of myself as the product manager and the whole ML ecosystem team. Massive thanks to you guys and the whole team. You've done an awesome job and played a huge role here. So thank you for today's talk, and thank you all the audience for watching and your great questions. Really appreciated it. As I say, this is the final talk of the year. So really best wishes for happy Christmas if you celebrate, and best wishes for a nice break if you're taking some time off. We'll be back in the new year, as I mentioned, with a brand new look, a brand new platform, some very exciting new topics, and a whole lot more. So stay tuned for comms on that, and make sure that as soon as you see that, you sign up for our tech talks, because once again, we'll have limited space. but a very interesting topic and a great opportunity for you to hear about the latest trends, technologies, and best practices from ARM and our ecosystem partners. So thank you so much for joining, and a Merry Christmas and a Happy New Year. We'll see you in 2023. Thanks so much, everyone.